talking about carboxylic acids and esters. So as always, here are the different kind of objectives that we'll be talking about today. It's the same as pretty much what we've done with all of our other functional groups up to this point. We'll talk about how we name them, different properties they have, some important reactions that they do. We'll also talk about some common names of these, how to name some of the salts that come from the reactions, and we'll do that for carboxylic acids and esters. And then we'll talk just really briefly about phosphate esters, as those will come into play again when we get to our biochemistry section. So up until now, we've done kind of these functional groups that are kind of their own thing. Carboxylic acids are the first functional group where it's kind of like a compound functional group, because what we see is a carboxylic group, a carboxylate group that we have here, has a carbonyl group in it, which is the C double bond to 2NO, and it also has a hydroxyl group. And so this whole group together is the carboxylate group. Now there are two different ways when you're doing your condensed form of writing the formula that you'll see this. You'll see it as COOH, which would be COOH, or sometimes written as CO2H, CO2H. And you just need to know that this is representing this structure right here. So carboxylic acids or carboxylate group containing compounds are found all over nature and biology, so they're very important, and we do need to understand what's going on with them. So here's just some examples of different ones that different carboxylic acids that we see in our day-to-day lives, including things like lactic acid and citric acid, which are both biological compounds in things like our muscles and foods, but they also exist in things like acetic acid, which is up here, also known as ethanoic acid, and this is essentially vinegar. The other important place where we will see carboxylic acids is, again, when we get to our biological compounds, and these are what we call fatty acids. So fatty acids, the reason they're called fatty is because they have these long hydrocarbon chains. So in terms of chemistry, when we refer to things that are fatty or fats, we're talking about these long chains here. Now, you can imagine that these have very long, lengthy names to them when we use their IUPAC naming system. So often they go by their common name. So this is lauric acid, stearic acid, things like that. You won't need to memorize your fatty acids in terms of their names. I will always provide those to you. Just understand that for purposes, especially when we get to our biological section, we end up using a lot of common names. The other thing too is to look at the polarity on this molecule. We have a polar head, right? You could think of this as like the head of the little tail. It kind of resembles a sperm if you look at it in that respect. Here's the head, here's the tail. The head is polar and water soluble, and the tail is hydrophobic, right? This is all hydrocarbons here, so this is non-polar. So we have a water soluble head and a non-water soluble tail. And this will be important when we talk about things like soaps. So go ahead and answer this question. Very good. So again, right, all three of these represent the different ways that we could have a carboxylate group. This is some sort of ester, it looks like, or ether, excuse me, ether. We're going to talk about esters in a little bit. So when we're naming these compounds, just like we've always done, we have to have the longest carbon chain that actually contains the carboxylate group. So on the chain, one of the carbons has to be that carbonyl carbon that attaches everything. So that will be determining your longest chain. We're always going to start with the carbon on the carbonyl chain of the carbonyl carbon of the carbon chain as number 1. So that makes it pretty easy in terms of your numbering system. The carboxylate will always be the number 1 position. The last E on the ending of, butene or bute, meth, prop, or prop, meth, eth, prop, bute, so on and so forth. We're going to chop off the E on that, and we're going to add oic acid to it. So if this was propane, right, prop, 1, 2, 3 carbons, we have prop, we're going to chop off the E and make it anoic acid, propanoic acid. Here we have 1, 2, 3, 4 carbons, so this would be butanoic acid. And then it also has a bromine on the 3 carbons, so 3-bromo, butanoic acid. We can also have things happen with carboxylic acids around things like our aromatic compounds or cyclical compounds. And so the same thing will still go on here. So this was a benzene ring, right? And so this becomes benzoic acid. And again, the carbon on the ring where that's going to be the number 1 carbon. So this would be 1, 2, 3, 4, and if we go the other way, 1, 2, 3, 4, 5. So 3 and 4 are better than 4 and 5. So this would be 3,4-dimethyl benzoic acid. So go ahead, take a minute, pause the video here, and try and name these compounds. Our first compound would be the 3-bromo butanoic acid. And the first one is the propanoic acid, the second one is the 3-bromo butanoic acid. Go ahead and name this compound. Butanoic acid again, right? We have 1, 2, 3, 4 carbons, so butanoic acid. This one's a little trickier, so go ahead and try and name this one. This is propandioic acid. So we look at how many carbons we have. Remember, in our line angle structure when we do this, there's a carbon here, here, and here. So 1, 2, 3 carbons. So we're going to have some sort of propane going on, but there's 2 acids on here. So this is going to have the dioic acid. Now, some of the physical properties of carboxylic acids follow a lot of the trends that we saw with our other polar compounds. Again, typically the smaller or lower molecular weight carboxylic acids will be liquids at room temperature. Most of these will be liquids at room temperature. When we start getting to things like our fatty acids, sometimes those will be solids at room temperature, and we'll talk about those later. And typically we say they have a sharp odor to them. So the best way I could describe this is when you smell vinegar. Vinegar is a carboxylic acid. Ethanoic acid, also known as acetic acid. That sharp smell from vinegar, that's what we're referring to. So that's something that you could kind of always, they'll have similar smells to that. Now the head of the carboxylic acid is very, very polar, and depending on what's on the tail, it could be polar or non-polar. So it depends. You have to look at the compound to determine that. Because of this polar head, which we're showing here, so here's 2 carboxylic acids. Their tails we're just leaving as an R group because it could be whatever. We're concerning ourselves with the head. So here's the C double bond O, here's the OH of one of them, here's the C double bond O and the OH of another. This special hydrogen bonding that they can do, we call this a dimer because 2 molecules can be attracted to each other in this form through this hydrogen bonding, right? So we know that hydrogen bonding, because it has hydrogen bonding and can form these dimers, it's going to have higher boiling points than what we see in an alcohol because we're forming 2 hydrogen bonds per 1 molecule, right? A hydrogen bond at the H of the OH and a hydrogen bond at the O of the C double bond O in both molecules. So we still see the same trend though. The bigger the carboxylic acid gets, the higher the melting point. So we see this general trend. We do have some slight discrepancies that occur in things like you can see here. This has to do with the overall structure of the molecule, but the general trend would be the bigger the molecular weight of the acid, the higher the boiling point. We can also look at solubilities, right? We know that relatively small acids, like these here, these carboxylic acids, right, they only have tiny little hydrocarbon tails to them, or no hydrocarbon tail at all. But as we start getting significantly bigger, this has, 12, 13 carbons in it, 14 carbons in it, or 15 carbons, 17 carbons, so on and so forth. Those hydrophobic tails start making it insoluble in water. That little polar head is no longer to be soluble when we have these big, big, long tails on them. Stearic acid, as we'll talk about later, is a fatty acid. This is basically the fat that we see in animal fat. So if you've ever cooked meat and the grease that is left over is not soluble in water, right? You have to wash it with soap as well. So to compare carboxylic acids to other functional groups of about the same molecular weight, we can see the general trend in their boiling points. So if we go to this same image that we've been using for all of our functional groups and we're just adding to it, we can see carboxylic acids are up here, again because of that hydrogen bonding and the dimers they can form. So these R groups, right, when we talked about the intermolecular, intermolecular forces, we can have carboxylic acids interact with other carboxylic acids, but they could also interact with water. So the smaller carboxylic acids, remember R is just representing some tail. If the R is small, like maybe only a CH3 group here or a CH2, CH3, there's a lot of interaction with water going on through hydrogen bonding, so it would be relatively soluble. As the R group gets bigger, if this was CH2 and there was 15 of those and then a CH3, now the nonpolar, the hydrophobicity of the R group is going to kind of win out over this solubility with the water and make the overall compound not soluble. So go ahead and answer this question. We call these dimers. Now, let's talk about some reactions. We've seen carboxylic acids before, especially when we were doing our oxidations with aldehydes. So we'll see that kind of reaction as well, but we're going to talk about some acid-base chemistry first. So carboxylic acids, as the name would suggest, are acidic compounds and will behave like acids. So go back to your Bronsted-Lowry definition of an acid. We know that that's going to be the proton donor. So because they're acids, when they're exposed to water, which would be acting as the base, accepting the proton, this would be donating it, we would end up with this overall structure and some H3O+. Now, oftentimes this O- is not stable, and we'll see it form a salt. So it'll actually make an ionic compound with some metal. And so we're going to go through, we created the anion here, and it can go react with a cation. So for example, if we have some sort of carboxylic acid with a base, right? NaOH is a base. The proton, the hydrogen, will be donated from the acid and will be accepted by the base. And when we do that, the H and the OH go make water. The Na is now a cation and becomes Na+, and the O becomes O-, the anion, and these two are attracted to each other. So what ends up happening here is we make a salt. This is actually considered a salt of this carboxylic acid. So this would be called sodium carboxylate. So what we do is we have the name of the cation, the metal, and then we're going to cut off and add this oxy-8 to it. And so we'll see some examples with this. So here is acetic acid, right? This is vinegar, essentially. And that's our acid with our strong base, and we're going to end up with sodium acetate. If we have benzoic acid and we have the base potassium hydroxide, we're going to end up with potassium benzoate. So we're going to chop off the ending of the acid, and we're going to add the word 8 to the end of it. So how would you answer this question? Again, heptanoic acid is going to be 7 carbons long. That's going to be the longest of the carbon chains, which means it would be the least soluble. Go ahead and answer this one. Correct answer here, we have to think of the fact that we have acetic acid that we lost the hydrogen for, and we'd have potassium acetate. So these carboxylic acid salts, right? When we have a carboxylic acid that is exposed to a strong base, we're going to end up with these salts. And so what we do is we cut off the ic acid portion of the name, and we add 8 to it. These salts are going to be solids at room temperature, and they're very, very soluble in water because they're now ionic. So even if this is a really long hydrocarbon chain here, we now have not just a polar compound, we actually have an anion because this is going to be O- here. So it's an ionic compound, so it's going to be very soluble in water, right? Ionic compounds, we know the secret language, the I know that you know that I know, that this is going to actually break down into the ions in water. So here's another example of that with stearic acid, right? Here's that really long chain. This compound here is, as it stands right here, is not soluble in water. But when exposed to a base and becomes the salt, it is soluble in water. So carboxylic acids are very, very important in things like our foods, as well as preservatives and medicines. So citric acid is used as a buffer oftentimes, but we also use it as a preservative. So you've probably seen on food labels citric acid, and maybe in parentheses it says preservative. And that's because citric acid can help stabilize some of these foods as a buffer. So go ahead and try and give the common name and the IUPAC name for the following salt. So this salt comes from this acid, which we know is acetic acid. We could also call this ethanoic acid, which means the salt of this would be sodium acetate, which would be the common name, or sodium ethanoate, which would be the IUPAC name. And again, we know it's the salt version of it because it's ending in -ate. So go ahead and answer this question. This would be lithium 4-chloro-2-fluoropentanoate. Another functional group that we're going to discuss are called esters. These are slightly different than ethers. They're still a sandwiched oxygen, but what makes an ester special is that one of the carbons on the sandwich of the oxygen is a carbonyl group. And that's because it's part of a reaction that comes from carboxylic acids. What we do to form an ester, it's the combination of a carboxylic acid and an alcohol. Now, if you're starting to feel overwhelmed with your functional groups and all the different kinds of reactions are going on, it's okay. There are a lot of them. I would encourage you to go ahead and start making some flashcards of the different reactions. So maybe on one side of the flashcard you'd have the name. So you'd say carboxylic acid plus alcohol. And on the other side of it would say the word, ester. And then another flashcard would be just this kind of general formula plus this leading to, the general formula of this. And then another flashcard might be, an actual example of a chemical where we don't have R groups there. And this is going to be really the way to kind of start learning these. You can't memorize every possible combination. So this is where organic chemistry is very, very different than what we've done so far in general chemistry. Organic chemistry is learning some rules. So learning these general rules of carboxylic acid plus alcohol yields ester, and then being able to look at any organic compounds and determine what the product would be based off of the rules and the reactants that are being put into it. So it's much more of a kind of problem-solving puzzle than it is a plug and chug. So while there's no math really that we deal with, it's still very, very challenging. The ester linkage is something that is very important, and we're going to see when we start dealing with proteins and amino acids and a lot in our biochemistry. So it's not something that we can ignore. So again, this ester linkage is the linkage between the O in the sandwich and the carbonyl carbon. Esters are very, very important in things like we said in biological compounds. They're also very, very common in things like smells and flavors. So a lot of flavoring agents, like if you have banana flavored Laffy Taffy or a pineapple flavored or scented candle, the things that are giving it the smell or taste of banana or pineapple, those are esters. So here's some examples of very common esters. So if you go and get a strawberry Jolly Rancher, this right here is what you're tasting that makes that kind of strawberry flavor, or if you have strawberry medicine or something like that. So it's a butanoic acid, so we have our carboxylic acid, and we have ethyl alcohol, right, or ethanol. And those come together to make ethyl butanoate. So what we do is we have our ester right here, and we kind of do each side of it. The ethyl from the alcohol and the butanoate from the butanoic acid. Here's salicylic acid with methyl alcohol, also known as methanol, right? So we get methyl from the alcohol and salicylate this is wintergreen. So if you have some wintergreen gum in your pocket, methyl salicylate is what's actually what you're tasting that's giving it that wintergreen flavor. We're not going to go too much into the polyesters, but you've probably heard of the word polyester before in terms of clothing, but what it is a polymer of esters. Just like we talked before with the concept of our polymers and polymerization, this is just doing it where our monomer is a carboxylic acid that gets combined with some alcohol, and we repeat this pattern over and over and over again. A few other kind of important carboxylic acid derivatives or kind of offshoots that we need to talk about are carboxylic acid chlorides, often referred to as just acid chlorides, and carboxylic acid anhydrides or acid anhydrides. These are very, very important in terms of chemistry and the reactions that occur because unlike the combination of an alcohol and an acid, this reaction, because we see the double arrow here, we can make the ester and then it can go back to being the carboxylic acid and the alcohol. And that's great if we wanted to think about a reversible reaction or one that could be broken apart. But oftentimes when you're in a lab, you don't want your reaction to break apart. And so we need to find a way to have it be a little more vigorous, a little more stable. And so what we'll do is we'll turn our carboxylic acids into either an acid chloride or we'll make it the anhydride version of it. And what this allows is when we react these with alcohols, we still get our ester, but we won't have a reversible reaction. So here's an example of that. This is an acid chloride, whatever our group is here, it doesn't matter, with the alcohol. We still get the ester, but now we get acid, HCl, instead of water, and this can only go in one direction. It won't reform this. Same thing with the anhydride. So what ends up happening is we'll get one ester and one carboxylic acid out of it. But again, this cannot reverse and go back to the carboxylic, the alcohol and the anhydride. So here's examples of that, real examples of that. Again, I would really, really encourage you to write a lot of flashcards for these and practice these. It's really the only way to internalize them. So if you want to give some practice, pause the video right here and try on your own to determine the structure of the ester that would be formed from this reaction of this alcohol and this carboxylic acid, and then try and name it as well. So when we do this, we're going to break this bond here. We have the OH, or we're going to break the H here, and we're going to have the OH from the alcohol here. And so those go off to make water, and in its place we're going to form this ester between the methyl group of the methanol and the rest of the carboxylic acid. So again, I would encourage you to pause the video here and try and determine what compounds you're going to get two out of this one because it's an anhydride this time of our acid. So the first product would be the ester, and you would also end up with the carboxylic acid of this side of it. So you would end up with this carboxylic acid as well. So during esterification, or the process of making an ester, a carboxylic acid reacts with blank in the presence of a catalyst. It would react with an alcohol. Can you name this or answer this? We would get an ester and a carboxylic acid out of this. So when we're naming esters, we kind of talked about this a little bit, it's kind of like how we name racehorses, if you have any knowledge of that. So typically when you name a racehorse, the reason racehorses have crazy names is because part of their name comes from the mother and part of their name comes from the father. The same thing is happening with an ester. Part of the name comes from the alcohol and part of the name comes from the carboxylic acid. So the first word in the ester is always going to be the name or the R group of the alcohol it came from. The second word is going to be the carboxylic acid, but instead of ic acid, we're going to change it to ate. So you can look at an ester and determine what reactants went into making this product. You should be comfortable being able to do that. You should be able to look at an ester and determine what two reactants, what alcohol, and what carboxylic acid were used to make those. So go ahead and try and name these esters. In our first one, right, we have ethanoate, or acetate is the common name for it, but basically here the ethyl came from methyl ethanoate, came from our alcohol and from our carboxylic acid, right? So when we go through this, we would have methyl ethanoate. The methanol is our alcohol, the ethanoic acid becomes the ethanoate, so we'd have methyl ethanoate. In our second compound, we had a phenol, right, our phenyl alcohol, and we had butanoic acid, so we're going to have phenyl, right, phenyl butanoate. And then in our last one, we had ethyl alcohol and benzoic acid, so we would have ethyl benzoate. So this is combining things from our chapter 11 and 12 as well as our esters chapter. So go ahead and name this compound. This would be our T-butyl benzenoate. Some students were asking how we do the isopropyl, the T-butyl, all those. It is very important that you go through and do your reading. We discuss it in depth in chapters 11 and 12, the T-butyl, the isopropyl, those namings. Now, let's go back to what we talked about earlier with this idea of, these reversible reactions. So let's say we have an ester, and we know that that came from an alcohol and a carboxylic acid, and we know that this reaction is reversible, or it could break apart. When we add water to an ester, we will get back the carboxylic acid and the alcohol that made it. This is a very important process that happens in our bodies all the time. This is part of how we digest animal fats. So, animals, other animals, and anyone who eats animal products, whether it's a person or another animal, will do a digestive process to break apart these esters into carboxylic acid and alcohols. And it's done through hydrolysis. One of the last things we're going to talk about in here is saponification. This is something that happens with the soap making process. So we talked about earlier this idea that when we have a carboxylic acid with a very long hydrocarbon chain on it, that very long hydrocarbon chain makes that carboxylic acid no longer soluble. But we did see that when we added a base to our fatty acids, right, these carboxylic acids with these long carbon chains, that we actually got an ionic compound out of it, and that the ionic compound is soluble. So same thing can happen with an ester. If we have an ester and we expose it to base, we're going to get the salt and alcohol out. So when we add water to an ester, we get an acid. When we add base to an ester, we get a salt. And in both cases, we would get the alcohol back out. So here's methyl benzenoate, an ester. When exposed to a strong base, we get sodium benzoate, right? We get the salt and the methyl alcohol back out. Again, here is the process by which this saponification happens. I will not be asking you in this class to go through and explain this. If you are going on to like a Chem 230, Chem 231 type class where you're actually doing organic chemistry, you will need to know these types of mechanisms. But for our class, you do not. So here is kind of our map going through the different processes and different products that you would get out. Again, these are really, really helpful for helping to navigate the different reactions that occur. So go ahead and answer this question. When we have an alcohol and we we know that it can form an ester with some sort of acid. We can get different kinds of acids. For example, if we have something like a phosphoric acid. This will be very important when we get to our biological portion, so I just kind of wanted to talk about this real quick so that you can see the different kinds of quote-unquote esters or ester-type bonds we could form. So we could have a phosphate ester, we could have a diester, or we could have a triester. This will be very, very important when we get to our biological sections, and we're talking about the compound ATP, so adenosine triphosphate, where we have these mono, di, and triesters that will form. So again, I'm not too concerned with you knowing these right now. It's just kind of to expose you to it so that when we do see them again in our biological section, it's not the first time that you're seeing it. This is also really important in like the sugar backbone of DNA. So we'll look at that as well. So a lot of these phosphate esters are really just crucial to our biological understanding of chemistry as we get going. Again, like we said, ADP, ATP, this is a part of energy and how we as people create energy and store energy in our bodies, and it's through phosphate group esters. And so we'll talk about this in more detail as we get going. So go ahead, try and answer this question. This would be a phosphate ester bond right here. Again, answer this question. We know that esters are formed from the alcohol, right? And that is the end of chapter 15. Please make sure you're working on your homework, checking out the extra help section. This coming week, we will be having quiz 8, which will be on chapters 13, 14, and a little bit of 15, but predominantly 13 and 14.